So good afternoon and welcome everyone to this NEASQC webinar. It's the third of a series of 9 between November and February next year. I'm Pascal Bernier-Bruna. I'm the communication leader for the NEASQC project and I will be your host today. So this webinar is recorded and you will receive the link to the recording on Monday. It's in listen-only mode because we have a lot of people registered, so it's easier that way. But you can use the Zoom Q&A panel to ask questions to the speakers, and you can see the questions asked by others. You can upvote them, you can comment on them, and the chat is also open to all attendees for more informal exchanges. So before I hand over to today's speakers, I would like to introduce the NEASQC research project and our use cases. I'll be as short as possible. So NEASQC stands for Next Applications of Quantum Computing. It's a 4-year project and it's funded by the Horizon 2020 program. And we are 12 partners in the NEASQC consortium, a mix of companies and research labs. And the objective of the project is to boost practical applications of quantum computing in the NEASQC era. So NEASQC is a use case centric project, and we have 9 use cases, and all are endorsed by an industrial partner and investigated by an integrated team of industrial and academic partners. So we have use cases in 3 big domains. We have use cases in chemistry, that's CO2 recapture and drug discovery. And if you have an interest in chemistry, you can attend our workshop that's going to take place at the EQTC conference. It's on the 1st of December. Then the second area is machine learning and optimization. That's where we are today. You see financial applications. That's today's topic. But we have 3 other use cases in this area. Reinforcement learning for stock management, hard optimization problems for energy management, and HPC mesh segmentation. And next week, we'll have a webinar about HPC mesh segmentation, so you can still register for that. And then the last domain is symbolic AI and graph algorithmics. And that covers quantum natural language processing, quantum probabilistic safety assessment, and quantum rule-based systems for breast cancer detection. So our project as a whole is committed to build a community with potential users of industrial NEASQC applications, and that's why we are organizing this webinar to share our knowledge, but mainly exchange beyond the project partners. So let's get on with today's agenda. And first, I would like to introduce Dr. Vedran Dunjko from Leiden University, who will moderate the session, the Q&A and discussion. In NEASQC, he's the work package leader for the machine learning and optimization use cases, and he deserves big thanks because he's not just the moderator, he organized this webinar and our other November webinars. So Vedran, could you explain how you built this agenda?
With pleasure. Thank you very much, Pascal, for your introduction. As you so nicely explained, the entire idea behind the NEASQC project is to really bring together industry and academic research with the overall objective to try to make use out of near-term quantum computers in the near term. And when we wrote the project, we kind of had an idea of what quantum technologies were available at the time and what kind of problems our industrial partners had. But time goes on and technology develops and we're discovering new things. Some ideas turn out to not work, some new ideas pop up. So in designing this webinar, we decided to invite experts which are roughly in the domain of interest of a particular partner in our use case, but not target very precisely specific questions that we have. We're more interested in what is possible out there. Following our talk by the invited external speaker, in this case, we're extremely happy to have Stefan Woerner, whom I'll introduce in more detail in a second. We will have our use case speakers from industry, in this case from the finance sector from HSBC, who are going to be discussing the types of financial computational problems they encounter in finance. And the main idea is then that after both talks, we spend something like 20 minutes talking all together in an open forum, driven by questions perhaps from the audience, to see whether we've discovered new or particularly well-suited matches between the problem and what quantum computers can possibly bring, or not. This is really an open forum. So to start off, it is really my pleasure to introduce Stefan Woerner, who is an IBM quantum application research and software lead. He's a principal research staff member in quantum technologies group of IBM Zurich. And he's been doing many things. His background is in applied mathematics, but now he's become really recognizable as one of very strongly industry-connected experts in topics in near-term quantum computing, specifically in quantum finance. And I'm very happy that you're here, Stefan, and I would like now to invite you to give us your presentation. 40 minutes are yours.
Thank you very much for the kind introduction and for the invitation, and welcome everybody to this presentation. So let me share my screen. All right. Yeah, I'd like to give you an overview of different applications that we looked into in the financial service sector, and where we think that quantum can make a difference. So I will not like deep dive into the different applications too much, but just give like the idea of why we think an advantage is possible, or what kind of an advantage, what are the challenges, and so on. And then I will refer to Stephen Maria later to also give more business context of what that would mean if we could realize that. Before diving into the applications, I'd like to very briefly talk about our development roadmap. And this has been published earlier this year, I think in February, and it shows how we plan to grow the quantum hardware over the time. And you see here the 27-qubit chips that we released in 2019, last year 65, this year, and I'll get back to that in a second, 127 qubits. And then you see these growing numbers up to over 1,000 qubits by 2023, which for us really marks an inflection point. On the one hand side, we think that that we reach a scale where first quantum advantages might be possible. It's very, very hard to say right now where exactly, but this is to be seen. But I think that we reach really system sizes that are really, really powerful to do first practical things. On the other hand, this also really marks the point where we can study first fault-tolerant, small fault-tolerant quantum computers, where we can first run first experiments of logical qubits. And then scaling beyond that, you see that up to 1,000+ qubits, this is on a single chip, and then going to the millions of qubits is likely then has to be via connecting multiple chips, quantum links, and so on. This is a hardware roadmap, but you also need to be able to use this hardware. And for that, we have this development roadmap on top of it. And in the previous years, the focus was more on running circuits. Now, since this year, we introduced the Qiskit runtime, which is now a containerized way to run programs. So here you would not run a single circuit, but we move one level up in the layers of abstraction. And you can write your own programs that leverage the quantum computer and that are way closer integrated to the quantum computer. And this is really crucial to be able to leverage this increasing number of qubits in a meaningful way. And then moving further up, or further into the future, here you see that the focus will go even further up the stack, really on focusing on application services. And of course, this Qiskit runtime is a crucial building block for that. Here, what we already released earlier this year are application modules, and we have one in Qiskit, our open source Python framework, on optimization, natural science, finance, and machine learning. I briefly come back to some of them later. And these are libraries that provide algorithms that can be used in these domains, and that allow a very easy way to get started, but that also allow to open the box and see what's happening and replace by own implementation. So it's also very modular to support the research. Now, just this week on Tuesday, we had the IBM Quantum Summit. You might have seen some announcements in the news from there, and I can recommend this. It's a 30-minute video about the IBM Quantum State of Union, which really recaps all these announcements and gives more details on the roadmap that I just mentioned. And you find this on YouTube. And I want to highlight the three main announcements from the summit from this week. The first, I think, is that we introduced performance metrics for quantum computers a few weeks ago. And this is really like how to measure scale, how to measure the quality, and then how to measure speed. You need to have all of that to really be able to run practically relevant applications. And at this summit, we had three big announcements on each of them. The first, I briefly touched on that before. We released our 127 qubit chip. It's the Eagle layout. Our layouts, our processor families are named after birds, and it's the IBM Washington chip. And the actual devices then are named after cities. Then this is for scale. Then on quality, we could show that we can increase in our experimental devices the coherence times close to even a millisecond, so really long, and the gate fidelities in the devices that we can get to 3 nines in the fidelity, so 0.999, which is also a huge milestone. We see here all these improvements over time to get really useful quantum computers. And the last, on the speed, I mentioned this, the Qiskit runtime. This is now available on all of our systems, and this allows to really provide a program that's run in a container in the cloud. And then, for example, if you know our queuing system, you're used to queue with circuits. If you move to a Qiskit runtime program, you're queuing with the program. And once the program is running, then the program is finished and you're staying at the front of the queue. And you can imagine that for variational algorithms, this is way faster. So this is not the main focus of today's presentation, but I think it is it's very, very important updates towards practical quantum computing. And I want to really recommend watching this short video if you're interested in more details on that. All right, now about applications, about quantum finance. I'd like to focus on 3 areas here and give examples of research projects that we have done, some of them by ourselves, some of them with partners from the financial industry. And let's start with simulation. When we talk about simulation in this context, we usually mean Monte Carlo simulation. And we briefly explain what this is. In Monte Carlo simulation, what you want to do is you want to, for a given distribution, let's say this one, you want to estimate certain properties of this, like the expectation value or some risk metrics, tail metrics. And you do this by just sampling from this distribution and counting or averaging. So it's a very, very easy algorithm. It's extremely generic. That's why it's also very popular, because for some things, it's the only thing you can do, because there are no analytic ways to handle some of these problems. And in the financial context, if we look at expectation values, we usually talk about pricing some asset or some derivative. If we talk about these risk measures, it's of course risk analysis. And Monte Carlo simulation is extremely generic, but the problem is, as you might know, that it converges relatively slowly. So you need many samples to get a decent accuracy. So to improve the estimation error by 1 order of magnitude, you need to increase the number of samples by 2 orders of magnitude. So this can lead to millions of samples depending on the problem, particularly in risk analysis. And here, a quantum computer can achieve a quadratic speedup. I'll briefly get back to the algorithm in a second. So when classically you need a few million samples, a quantum computer may only need a few thousand. And depending on the application, and here one has to be careful, but depending on the application, this can make a huge difference. And I guess we hear more from our colleagues from HSBC later. We tested this on a simple example here on the real quantum device. This was actually just flipping an unfair coin. And you see on the number of samples in the x-axis and the resulting estimation error, how Monte Carlo scales and how the quantum algorithm scales. And you see that this quickly outperforms it. This chart here, I will get back to that. One has to be a bit careful how to interpret this. But this is the idea, and this is why there might be a potential advantage. Now, how do you model these problems? Just to give you a little bit of intuition. let's suppose we have a very, very simple financial model. There's just something with a certain probability you get a high stock value, for example, stock price, or a low stock price. So this is a single period binomial tree if you want, or could be something default or not. And that we can map on a qubit. And this state here that's indicated on the blob sphere, if you would measure that, and you would actually get with a 70% probability a 0 or with a 30% probability a 1. Now this is of course a trivial distribution, but if you use more qubits and you entangle them, then you can build in principle arbitrary distributions. All right, and once you have that, then we can use a quantum computer to actually estimate properties like the expected value of this random variable that we define like that in a set of qubits. And how do we do this? We leverage an algorithm called quantum amplitude estimation. And this is a really a canonical, or like this was a seminal paper in 2000 by Prasad et al. And it shows how to simulate such systems, and this is what happens here at the bottom. So this is where the actual simulation happens, and these Q operators, you can think of them as quantum samples. So every operator here corresponds to one, what I called quantum sample earlier. So this is where the simulation happens, but then you need to read out these results somehow, and this is what's happening at the top. So in a way, you extract, not fully true, but you can think of that as extracting one bit of your result at a time here. And the more bits you want, the more you have to work. Then in the end here, you have the result encoded in the quantum state, but then you apply a Fourier transform or an inverse Fourier transform to actually read it out such that you can measure it. But simplified, this bottom part is the actual simulation, and the upper part is the overhead to extract the results. And there was a lot of research in the last 2-3 years to actually improve that. So there was about almost 20 years no progress, and then when we realized what we can use this for, there were like really a series of papers now pushing that and improving that. The first one was actually by colleagues of mine in Tokyo and their partners, where they could get rid of all this upper part and only focus on the green part. And this algorithm is then called maximum likelihood amplitude estimation. And this is a very neat algorithm. It has a good performance. It has these simplified circuits, but it still like has a lack of theory. Like it's providing lower bounds on the estimation errors and not upper bounds as you would usually like to have. Then there was a paper a bit later in the same year, both 2019, on the same topic, where they actually also had these simplified circuits. Now a rigorous theory, and the asymptotic scaling of this algorithm is still by far or not by far, but it's the best. So it's the only one that can take out a logarithmic factor that all the others have. But the constants are really, really impractically large. So it's theoretically a very interesting algorithm, but practically not. Then in the same year, again, December 2019, we could come up with an algorithm that we called iterative quantum amplitude estimation, that actually now combines all these things, has simplified circuits, good performance, and a rigorous theory. And you see how this builds on top of each other and how this is driving the field now that we have an idea about where we could possibly apply these things. We implemented that and tested this for illustrative examples. And you see here on the x-axis again the number of samples or oracle calls and the resulting estimation error on the y-axis. In blue, you have as a reference the classical Monte Carlo. Then in red, you have the one that has as a first algorithm really the rigorous theory without the red box on the previous slide. But you see, it's like even for ridiculously high accuracies, it's still not requiring less samples than classical Monte Carlo because of the constants, but the slope is steeper. And we have the canonical amplitude estimation in this lighter blue, and then maximum likelihood amplitude estimation, and then the iterative one in dark green, which I think we could slightly improve this actually since then as well. So this gives you an idea of how we need to push that, and this might not look like a huge improvement here, but I get back to that in a second why this is still very relevant. So this was one stream that we want to improve these fundamental algorithms, The other stream of research is how can we actually model problems such that we can use these algorithms for practically relevant things. And here we looked into option pricing, and we looked into how to take an option contract or a derivative contract and map this to a quantum circuit that's then accessible to this amplitude estimation. That's the one question. The other is then, I mean, if you have a statistical process, a stochastic process or statistical model, how can you map this to a circuit? So the one is the contract, the other is kind of the stock market. And here we looked into these things more conceptually. Do we find things that in principle should scale? But then more recently, with our collaborators at Goldman Sachs, we looked into how does this scale for practically relevant applications. And here we picked two derivatives, autocallables and TARFs. It doesn't really matter how they work in detail. They're both time dependent or path dependent. So it's not only important where the stock price ends after a certain time, but the whole development of the stock price is important for the payoff of this derivatives. And what we did is we looked into this. We got from the business some data on what they would like to have, like what's a result or what's an estimation error that would be okay. How fast should this pricing work? And here the baseline was like it should be faster than a second. And then we wanted to understand for these target accuracies and these specifications, what's actually the requirement on a quantum computer. And what you see is that these numbers are pretty high. So the T-gate, which is the limiting factor for a fault-tolerant quantum computer. So here we're definitely talking about a fault-tolerant quantum computer. It's around 10 to the 10 T-gates with a depth. So if you assume that you can run some in parallel of 10 to the 7, 10 to the 8 on around 10,000 logical qubits. So this tells you it's not so near term, this application. This is requiring a logical or fault-tolerant quantum computer with a significant number of qubits and with the capability of running T-gates in parallel. And if we pull all this together, then we find that we actually don't meet this 1 second goal. We are about a factor of thousands too slow. Now, this might on the first glance be discouraging, but I wouldn't say so. Because this was the first time that we really measured that we really took a practical problem and tried to understand what is the circuit complexity and the algorithm complexity. And since then, we actually could push this further, we could improve the algorithms. I think just in the year where we wrote this paper, we already could achieve a 10x improvement, otherwise we would be 10,000 times too slow. And this is very important because this now shows us where are the bottlenecks, where do we need to improve, and it also helps us guide which applications might be really the ones where this algorithm makes sense. One point that I haven't really touched on, you might wonder, why is this the case? Why is this a factor of 1,000 too slow? If I said earlier, it requires a significantly smaller number of samples. The reason is that a fault-tolerant quantum computer runs at a significantly lower frequency than a classical computer. Classically, we have gigahertz and so on. A fault-tolerant quantum computer has a T-gate rate, so that's why we measure here the T-gate, what's expected from everything we know today, of 10 kilohertz. So there's some order of magnitude difference in the frequency that these machines run at. And so it requires significantly less operations, but every operation is slower. And then this really needs to be balanced. And every factor, constant factor that we can squeeze out of it helps us to make a step closer to the application, to the practical relevant application. And I guess we'll hear later from Maria and Steve what that would mean in the business if we can get from 2, like let's say we can cut this down by a factor of 2 or something like that. All right, so much about the simulation. We have in Qiskit these application modules that I mentioned before. We have Qiskit Finance. And here you have a couple of examples that actually implement these options. You can see how this maps to contracts. You can specify them. and play with these algorithms. This doesn't scale to any like to the 10,000 qubits that I mentioned before, because we couldn't even like simulate them, of course. But in a small scale, for some illustrative examples, this shows you how you can do that. There are Jupyter notebooks that you can use right away, simulate for small problems, maybe also test on real hardware. All right. Second topic is machine learning. And here I usually start with this disclaimer. The quantum computer has a huge state space, right? This grows exponentially with the number of qubits, but that does not necessarily mean that it can handle big data. Because if you have big data, you first have to load this somehow in the quantum computer. And depending on what you do in this data, you also then have to read out the result. And if you're not careful and if you're not analyzing what you want to do end to end, then these can be bottlenecks that can actually fully diminish the quantum advantage. So here one always has to be very careful and look at this end to end. An application where we think that this might be possible is actually classification, so supervised machine learning. And so if you have a labeled data set, you want to train a classifier such that for a new data point, you can easily say, is it in the one class or in the other class? If you can do this reliably, then there are plenty of applications. I just listed a few that are relevant in finance, like fraud detection or credit risk rating, things like that. And classically, you can use a support vector machine, which essentially computes this hyperplane that separates these two classes with a maximum margin. And then if you have a new data point, that's of course easy to tell whether it's left or right of that. But the problem is if data is not looking that nice, if it's not linearly separable, then what do you do? And probably I've heard about that from classical machine learning. You can apply feature maps. So you take this set, and you now see here there's no line that separates it. You map it to a higher dimensional space by using a feature map, and now you can separate it again. And what you can now do with the quantum computers, you can, instead of a classical feature map, use a quantum feature map. So you take a classical data point and you prepare a corresponding quantum state, which can now be in an exponentially higher dimensional feature space. And this might be very interesting for some applications to get a better performance. Now, what do we mean by a quantum feature map? That can be, for example, a parameterized quantum circuit like that one that takes as the parameters the features of your data point. And then if you plug these parameters in, then this is a fully defined circuit, and the resulting quantum state is then a representation in this feature space of your original data point. This has been suggested by colleagues of mine in IBM Research in Yorktown, and they have suggested that you can use such feature maps, or more precisely the inner product of these two feature states, so a quantum kernel in a classical support vector machine. So you actually use a quantum kernel, and if you can evaluate that, you can use the classical code for support vector machines. And earlier this year, or I think preprint was end of last year, our colleagues could even prove formally that such a classical support vector machine equipped with a quantum kernel or a quantum feature map can achieve a rigorously proven quantum speedup. Now, this is, I don't go into details here because this is a problem based on discrete logarithms. So it's a very artificial problem, but for such a strong statement that you really can prove that with a quantum computer, you can do this in polynomial time, and with a classical computer, assuming that discrete logarithms are difficult classically, you can only do this in exponential time. This is, of course, an extremely strong statement, and for that you need some assumptions. But this is a very strong motivation for these kind of models, for these quantum feature maps and kernels and quantum support vector machines. There are different ways to use that. You can also use these feature maps in quantum neural networks. There are different names for that. I usually use that at the moment. So here you use this quantum feature map that takes your classical data point and prepares a corresponding quantum state. Then you have a variational circuit. So it's again a parameterized quantum circuit, but now you train these parameters. Then you measure, which gives you a bit string, and then you map this bit string to a certain value depending on your application. And depending on your application, you might measure here a couple of times an average over your measurements or something like that. And if you think of this as a black box, it takes an input, a data input, has some trainable parameters, and gives you some output. So you can then train this as a black box in supervised machine learning, for example. Just because you can do that, that does not necessarily tell you whether it's a good idea to do that. So this is at the moment something that's very actively studied in the community. And one result or one paper that we wrote and where we looked into is how to quantify the power of these quantum neural networks. And here we use the concept from math that you might have heard about, the fractional dimension. Here we illustrate this using clouds. You might have heard that a cloud, I mean, it occupies obviously a three-dimensional space, but it only has a dimension of 1.37. So it only occupies a sub or fractional dimension. It's a lower dimensional space that it lives in. And we used a similar concept to define this effective dimension, or this effective dimension is based on this concept. And it kind of measures how effective the parameters of your model are used. So the more effective these parameters are, the more expressive your model is. Or if the model is more effective overall, maybe you can get the same with less number of parameters. So there's another nice thing of this effective dimension, that it's taking into account the size of your training data set. And you can think of that as a resolution, like the more training data you have, the finer details you can resolve. And what we did then is we took this effective dimension and we trained, or we looked at classical and quantum neural networks. And this is what we found. So on the x-axis, you have here the number of data. And on the y-axis, you have the normalized effective dimension. So 1 would mean that all parameters of your model, all trainable parameters, are effective. What you see here is that the classical neural networks, and here we picked classical neural networks that had the same number of trainable parameters than the quantum neural networks, and we enumerated over all possible configurations. And we picked the best one. So you see that the classical neural networks have a normalized effective dimension around 60% or up to 1 million data points. Then we looked at 2 different classical quantum neural networks, one with a feature map that's kind of trivial and one with a feature map that's known to be difficult classically. And you see that the effective dimension grows with that. And this quantum neural network that we, with a difficult quantum feature map, really had a very high effective dimension. So it's making the most effective use of the trainable parameters, like 90%. And this is a very interesting insight. It's not, one has to be careful what this actually implies and how to use that. But it definitely shows there is something different in quantum neural networks than classical neural networks. And this effective dimension has also a geometric interpretation. It's depending on the loss function, it's closely linked to the Hessian. So a high effective dimension actually also then implies a nice loss landscape for training. This is what you see here on the right-hand side. We trained this for a very simple data set to test. And you see the training iterations on the x-axis and the resulting loss value on the y-axis. And the quantum neural network really converged way faster to a better value than the others. And the black line here is the same on a real quantum device on 4 qubits. So here we could even train this on a real quantum computer. We actually reduced the entanglement a little bit because of the limited connectivity of the hardware, and that even improved over the simulation here. That's why there's a little bit of discrepancy. So if you can do that, if you have such a high effective dimension, of course, there's always the question of generalization or memorization, or whether you just learn your data or whether you really learn the relationships. This is something that is all like open research, but we definitely see that they do behave different. They seem to have here favorable properties. I know that also in a recent publication from Vedran, they also looked into generalization and also found positive positive behavior there. So it really seems like quantum neural networks are something that we need to investigate and that can have really an advantage in the quality of these models in terms of generalization and possibly also training speed. But these are first indications of what we may find. So next step is really to scale this and benchmark this on larger and more practical applications. Also other quantum neural network architectures. Here I don't want to go into details. We looked into quantum Boltzmann machines, for example. Here I just want to highlight an application. We looked at a simplified credit card fraud data set, and we trained this Boltzmann machine, this quantum Boltzmann machine on it. And we also trained different classical machine learning models just out of the box. So for none of these models, we did any hyperparameter tweaking or whatever. But you see that for this test case, the quantum Boltzmann machine actually outperformed all the others. And that was a quite nice result. It's in machine learning, it's rather difficult to say how this generalizes to larger problems. I think this is something we have to also study further, but I think it's a promising first proof point in what kind of direction this can go and where or what kind of advantage we may find and hope to find. So it's not about necessarily handling larger data. It's not. It's really about having a higher accuracy or a better generalization, better learning, essentially. All right. We also have Qiskit machine learning, and Qiskit machine learning provides these things that I mentioned as different building blocks. We have computational building blocks like these neural networks or quantum neural networks and kernels. And then we have different algorithms on top of that leverage these, for example, for regression and classification. And then we also have a torch connector that takes neural networks and makes them available as PyTorch modules. So you can then use them in your larger PyTorch workflow as just one node in a network. And this is, I think, a very interesting application area that we are studying and where we need to better understand where and how quantum nodes in a larger machine learning workflow really can be beneficial. Okay, now to the last application area I want to cover, optimization. Here we usually talk about quadratic unconstrained binary optimization of QBOs. So the name says already what this is about. We are optimizing binary variables and we want to minimize a quadratic objective function. We do not have any constraints. This unconstrained can be relaxed a little bit, like we can add linear equality constraints by adding quadratic penalty terms to the objective. But then that's it. So it's a relatively easy to define problem class, but it already covers many interesting things like portfolio optimization, feature selection, max car traveling salesman problem, things like that. And the heuristics to solve this on a near-term quantum computer are usually all of this structure. So we map the problem into an Hamiltonian, and then we use a variational algorithm to find the ground state or to approximate the ground state. So we have a parameterized quantum circuit that prepares the state. And if we have this state prepared, we measure that on a quantum computer. This helps us to estimate this expectation value, and then we minimize these parameters. What's important on this slide is the word heuristic. So for near-term quantum optimization, we usually do not have much guarantees about the performance. So if you now think about this in a practical application, we just have to demonstrate that this outperforms on classical. If we apply this now with a growing hardware, and this is something that will happen over the next years, then we can start benchmarking, we can start making projections. But I think this is really something that's going to start now. With the smaller hardware, let's say if you run an experiment up to 10 qubits, 20 qubits, since this is all sampling based, to have a smooth landscape, so to have enough samples to handle the shot noise itself, you already have such a high probability to find the optimal solution that the benchmarking is pretty difficult to get a meaningful result here. But now with colleagues of mine just published a paper where they could solve a problem with 40 binary variables. Now 2 to the 40 is already a relatively large number. So there you can already start, like you're at a scale where you can start seeing the beginning of the asymptotic behavior. I think this will be really exciting in the next year, the next years, to see how this scales. And then if you see this asymptotic behavior, then you can make these projections, and then you can really make good forecasts on when to expect the heuristic to outperform the classical heuristics. I mentioned that we don't have any guarantees, but we try to get some anyhow. And this is why we looked into warm starting quantum optimization. And the idea of warm starting is that you use one solver to provide a good guess, an initial guess, to kick off another solver. And what we did is we used classical solvers, and I'll illustrate this in a bit to explain the idea, to warm start a quantum solver. And if this is our quadratic program and our QUBO, this is like the one of the easiest you can think. It's the most complex one I could easily visualize. So you have two binary variables, and here in this example, of course, the optimal solution is setting both to 0. That's here to minimize. What you can do is you can now just drop this constraint that the variables have to be binary and also allow continuous values in between. Then you end up with this. And that you can easily solve, because in this case, this is convex. You can do this classically. You get a solution which would be 0.25, 0.25. Now with this continuous solution, what you can do is you can construct a quantum circuit that kind of starts in this continuous solution. So you can use superposition to mimic continuous solutions, and then you can start your quantum optimization algorithm from there. So you initialize your quantum circuit in a very special way. And this allows you to get solutions for this problem. Now, this relaxation going from binary to continuous, this is kind of the naive relaxation that actually already did work better than doing no warm starting. But you can, like classically, you can do much better than that. Like you can use semi-definite programming relaxations. For MaxCut, there's a famous Gilman-Williamson algorithm, for example, which I think was one of the first with a proven and under some assumptions optimal approximation ratio. So what you can do is you solve an SDP, and then you can do randomized bounding from that, and then you get solutions that often have a theory that tells you, for the MaxCut case, that you are 88% optimal. So the average of your samples will be at least 88% of the global optimal solution. And what we can do now with this warm starting is we can actually start our algorithm from there. So we take the samples from the classical SDP relaxation, and we start our quantum algorithm from there. And this gives us a kind of the trivial guarantee that we are at least not worse than that. So we can only improve upon that or get like the solution that is as good as the classical. And in our test cases, we could actually show that we could significantly improve upon them in many cases, and got for MaxCut problems significantly closer to the global optimum. So this might be a very promising approach to get advantages in near-term quantum optimization. But it also tells you very clearly what type of advantage that is. Since you first run your classical algorithm, it's certainly not an advantage in speed. It's an advantage in the quality of the solution. So really you get a better result. But since you run a second step after the classical one, it likely takes longer to get there. So we're definitely not talking about high frequency trading or anything like that. We also have Qiskit optimization, and Qiskit optimization provides a modeling layer. So you have DOCplex, which is a very nice modeling language. You can more or less write down your mathematical formulas, convert them into a quadratic program. And then you have different algorithms that all implement the same interface, so that you can easily compare the performance of different algorithms. We have classical algorithms to benchmark and test and validate. We have quantum algorithms, and they can even run, like you can go directly from there and run that on the real hardware. And we'll actually release soon also a Qiskit runtime program for some of these that makes it very easy to also use some more advanced compilation and error mitigation techniques and really try to get the most out of the hardware that we have today. With that, I'm also at the end of my presentation. So just to wrap up, I think last year or the year before, we published this review paper, which kind of puts the things that I mentioned in a bit context and gives some more details. And if you want the starting point to dive deeper, that might be a very good paper to have a look. And it discusses all these areas. And with that, thank you very much for your attention.
Thank you very much, Stefan, for this really fascinating and impressive talk. We have a little bit of time for questions. And I'm going to start with one question from the chat, which is from Tracy, quite a general question. There are two schools of thought, whether or not quantum computers will be able to predict stock market prices in the future. What would you say? Will they be able to or not?
I think we have to be very careful in quantum machine learning not to treat it as the crystal ball who can predict everything. So quantum machine learning has a potentially give an advantage in data sets that have a complex structure. And in stock market prices, I think the problem is that you need to take into account a lot of information. There are a lot of things that can happen that you just cannot really predict. So I think in predicting stock market prices, I would be a little bit more skeptical. Might be other things like fraud detection where I think that could be more promising. And the second problem with predicting stock market prices is also possibly loading the data, but that's difficult to say. I would be a little bit conservative on that question.
Thank you for the answer. So I've done a quick scan of these other questions, and I think they're fitting really nicely for the discussion section after we've heard our HSBC speakers.
There is one in the Q&A panel also. Did you see it? Okay.
Yeah, I have keeping
okay.
Thank you, Pascal. I think they're actually very good questions for after
okay.
this talk of Maria and Steve. So then with this, I will then introduce our HSBC speakers. So it's my pleasure to introduce Steve Suarez, who's going to be speaking first, and then following by Maria Nogueiras. So Steve is a global head of innovation and global functions at HSBC, and he's been working for close to 30 years now as a transformation expert in consulting, telecommunication, financial services, and so on. And he has a proven passion for innovation and growth. So I'm really excited to hear what he's going to be thinking about quantum computers. And Maria, she, well, not dissimilar to Stefan, has a background in actually applied mathematics and has been working for many years now in financial industry and quantitative areas, specifically for HSBC, as head of traded risk management development, traded risk model development for foreign exchange and equity. So with this, it's really a pleasure to have you. Steve, the floor is yours.
Thank you very much. And I guess you've heard my background. I've obviously a lot in the change, the transformation, and recently in the innovation space. So part of my role at the bank is I look for and I identify emerging technologies or disruptive technologies. So that's why quantum computing is such a fascinating topic to understand and to see how we're going to leverage it for the company and ultimately for our customers. So within NEASQC, we're focusing on some very specific use cases in finance, such as option pricing. But however, we're looking and also exploring more wide applications within the financial services industry, such as Monte Carlo simulation, quantum machine learning, optimization problems. So we've got things like optimization pricing or collateral optimization. At the bank, we're also looking to see how do we leverage these techniques I think Stefan mentioned fraud detection. So that's a great example of one of the things that we're looking at, as well as risk management is where I came from over the last couple of years, and also doing things like reverse stress testing. So we're very keen on this, and actually the industry is very excited, and being in the financial service industry right now, when it comes to quantum, it's exciting times, right? So we want to see if we reach, or when we reach, and we can talk about that with Stefan afterwards, quantum advantage, and make sure that we can take advantage of all that it has to offer once it's mature enough and we can use the technologies. Part of my role is to make sure that we're preparing our people, educating them on their capabilities, and also doing the upskilling that we need. This is new technology. We're all learning through it. And as a business user, we want to make sure that the business people understand both the capabilities and what it can get done, but also our technology people, and we want them to understand on how would you program in quantum computing, because as we understand it, it will be different, and we want to make sure that we're doing that now. So we don't want to be in a situation where we're in a standstill, and once the technology hits, we start going from there. We want to make sure that we're hitting the ground running. But we also want to make sure that we're setting the right expectations. In my role in innovation, I deal with a lot of people that try to sell me services and build up the hype and say, look, I've got this thing, you push this button, you can actually predict stock prices, or you can do this, and some of it is hype. And so part of the role is to understand, okay, what is truly hype and what is reality? What can we do and by when? And it's not only that, understanding what are the great use cases, or how do we apply quantum computing versus classical computing, and sometimes how do we look at a hybrid approach, right? So it's not like we're going to get a quantum computer and then put everything onto that computer. It's really for narrow specific use cases where we think the advantage will come, and then continue to use our classical computing, cloud computing, where it's needed. And so that's why for us, timing is key. Making sure you get the time right? You don't going early or putting a lot of money early. You could sit there and spend a lot of money, but then coming too late, and that's definitely somewhere where we don't want to be as an organization. So part of it is really understanding what platforms are out there. And for us, we want to be platform independent, and we want to really understand the landscape because of the uncertainty of the technology stack, both the hardware and software. We're looking at different quantum computing programs, such as Google, IBM, Microsoft, Atos, and others, just to name a few. And so what we're looking for are platforms that are user-friendly, that are generic. We do want to be hardware agnostic, and we're looking for platforms that have known algorithms, that people have an active community of developers where they can share best practices and share tips. So as mentioned earlier, we're keeping an eye on all the different technologies. Being such a large organization, we want to make sure that we can take advantage of it. But as a bank, we're also looking to partner up with academia, with other vendors, other startups, to take a look and make sure that we're engaged in that quantum ecosystem across the spectrum. So with that, I wanted to kind of just set the stage and give you a sense of how we're looking at it, how we're starting off and structuring ourselves. I think from a more technical perspective on some of the use cases I mentioned, Maria is the perfect person that can sit there and explain that to you. And then I'm looking forward to answer any of your questions later down in the conversation. So thank you very much. Maria, can I pass it over to you?
Sure. Thank you, Steve. Let me just share my screen. 1 second. Are you seeing my presentation?
Yes.
Yes, but it's not full screen.
Okay, let me. Okay, so thank you very much for the invitation, Vedran, Pascal, and thank you very much for the great talk, Stefan. I will just try to use the few minutes I got for highlighting the importance of the problems that Stefan explained and the huge benefit that they could bring to the banks in case that the quantum computing really can help us to build more efficient algorithms. In particular, I will focus on his first topic, simulation, or more in particular, Monte Carlo for option pricing. Here, for the few in the audience that have not a financial background, I'm just giving a quick overview of the problem. So we are interested into pricing options. Options are financial contracts whose cash flows, the payments depend non-linearly on the performance of some underlying assets. We call them like that, underlined. That could be stocks, interest rate, exchange rates, and etc. So, and our objective is to compute a fair value for these contracts. We can formulate this pricing problem as an stochastic differential equation that gives us the evolution of the underlying assets, together with a payoff function that characterizes, in fact, the option, because defines the payments as a function of the underlying realizations. And finally, the value of this option, the fair value, is not more than an expected value of the cash flows, in the right probability measure, and etc. But is kind of as simple as that. I have written here in red an example that is one of the simplest one, because for this one in particular we got an analytical solution, but this is not the general case, and in fact we are interested in the more complex problems for which numerical approximation for the solution of this expectation is required. Where the complexity is coming from, as Stefan explained, for many derivatives or options, the payoff function depends on the whole realization, whole path of the underlying assets. So that gives further complexity to the problem. We can have not one, but several underlying assets. So we have a multidimensional problem. And in general as well, for getting a fair value, we might need a more complex stochastic differential process here with stochastic volatility, for instance, and etc. So the problem is in general complex, and we need the numerical approximations. In many cases, not always, we use the method that as well he explained, that is Monte Carlo, that is as simple as discretizing the stochastic differential equation by sampling and then computing the discrete average of the realizations of the payoff on those samples. That will give us an approximation of the value that we have defined previously. So this option pricing problem is important for many or several areas within a bank, but I will give you an example from the trade risk area where I work. Here we look at portfolios, so sets of derivatives, including options, and we want to estimate the distribution of P&Ls, profit and losses, or in other words, we want to estimate the distribution of the values of this given portfolio in some future time horizon or several time horizons. And for this as well, very simply, we need to identify the assets or risk factors underlying this portfolio of derivatives. We forecast those, we give estimations of the distributions of those risk factors. Then we reprice the whole portfolio in those scenarios, aggregate and infer some statistics, and that would be it. These problems that might ring a bell, that arise in market risk or in counterparty credit risk, they are very big in general. I'm going to give you even a more detailed example from the counterparty credit risk world. In the counterparty credit risk, the risk we want to prevent here is that our counterparty defaults when the portfolio has a high value, when the counterparty owns money to us. So in this profit and loss distribution that I was speaking about here, we are looking into the profit tail. And let's give you an example with numbers. Let's consider an example that could have, that depends on the bank, on the portfolio, on the case, but could have around 1 million trades. Many of them will be options. The bull part of the options will be priced with Monte Carlo. For this particular problem in counterparty credit risk, we need to compute this distribution of profit and losses in many time horizons, from now till the last expiry time of the trades in the portfolio. So that could be 200 time horizons and a number of paths that I'm giving here a number like 10,000. So that would give us like around 2 million of points of scenarios where we need to first simulate the risk factors. And as well, I'm inventing here a number that could be consistent with these 1 million trades. 50,000, we should simulate these risk factors. And then in every one of these 2 million scenarios, we should reprice our portfolio. And in many cases, then we should apply a Monte Carlo using these 25,000 million paths. So what we are plotting here, in fact, is a nested Monte Carlo. Even powerful classical computers need to run for several hours overnight, usually, in order to complete these tasks. At the end, we are going to compute some statistics of these numbers, like a quantile. And we often require approximations, simplifications in order to get those numbers. That could be reducing the number of Monte Carlo simulations, therefore reducing the accuracy. And not only that, this will be only the basic problem, because we usually want to go further. We need in fact to compute the sensitivities of the risk number with respect to some parameters. Which parameters here are we talking about? The volatilities on the underlying risk factors, the level of the risk. That means that we need to modify a little bit one of these input parameters. In mathematical terms, there will be the T0 values of the stochastic differential equation, and run the whole process again. Compute the same number, and then the difference, that could be the sensitivity. So at the end, we should repeat this. And I did not want to complicate this problem further, but could be further complicated, because in some use cases related to this, we need to compute the sensitivities as well, but the sensitivities of the option prices within this simulation path. That would be, again, repeating this process a number of times. That currently is not feasible, so different numerical approximations and alternatives are required. And of course, the $1 million question would be, and I think Stefan already started to answer us, whether the quantum computing could help us into speed up the Monte Carlo, and in particular could help us with the kind of problems that I just described. In this slide, I just wanted to give an overview on the quantum Monte Carlo from a non-expert perspective, but I think Stefan already covered that. So what I might like to highlight only are maybe the caveats, the caveats that could help us in the follow-up conversation with Stefan. He already mentioned that for this particular use case, the current technology, noisy quantum computers, don't seem feasible for solving that. So of course, we from the bank would be interested into by when, and if we can give an estimation there of how. And maybe second point that he as well mentioned, but I would like to as well highlight here is that the Monte Carlo, if you are new to the field, to the quantum computing, and you work for finance, maybe the first message that we'll receive is that Monte Carlo is offering or is promising this theoretical quadratic speed up compared to the classical, and that of course is very appealing, because that would mean that instead of millions of simulations, we would require thousands, and that could be extremely interesting for us. But of course, we want to know whether that would be possible in practice. And as well, Stefan already touched upon this point. But anyways, I will highlight the following. After this year or so, collaborating with the universities on this specific topic, what we have learned is that many times when in the literature they talk about this quadratic speed up and etc., they are referring mostly to the part of the quantum Monte Carlo that extracts the expectation that is related to this quantum amplitude estimation algorithm that Stefan explained to us. But they are not always referring, they are not referring to maybe the bottleneck, or we think that it could be one of the challenges, and I think that Stefan has already explained that before, that is this loading distribution problem that is the the wording that sometimes you can find in the quantum computing literature. That form from the classical Monte Carlo point of view is the sampling. So the sampling problem, the simulation is not fully solved, and we are starting to see some papers like the one from Stefan and his colleagues that are looking into specific problems and providing solutions for that. But I would say, and as well, I would like to hear from Stefan for sure, that this is not fully resolved. It's still a challenge in the general case for sure. And I'm borrowing a paragraph from one of his recent papers where is stated exactly this, no? That although preparing such states is in principle always possible for reasonable stochastic processes, efficient realization of this method demands a careful analysis and may not always result in a practical quantum advantage. So I think this is very revealing and important for us, because from the industry, as Steve just said, we really want to understand what are the possibilities and where are the challenges or the bottlenecks. That is crucial for us, and of course we are doing that. And maybe to finalize with a little bit of advertising, because as I said, we have been collaborating through the NEASQC project with the CESGA and the Universidad de La Coruña over the last year or so, and thanks to them we have been learning a lot. I might give the last comment that might be a bit controversial, because I know that Stefan might disagree. I believe, and we believe, that one of the issues with the quantum computing, not only applied to finance, is that currently might be a huge distance or important distance between the knowledge of the experts on the area, like him, and the rest of the world that we are trying to get there. And that, you know, of course, we know that there are several initiatives like the IBM, the Qiskit, and etc., free source codes that are trying to help on reducing that bridge. This project itself, the NEASQC project, I think has as an objective to create a community of experts. But we believe that this is still an issue. It's not that easy for someone with no theoretical physics background to understand the papers to the full. So as well, I mean, I would like to bring this out because maybe that generates a little controversy. But anyways, I think we are on our way. And sorry, I will end up here if you wish.
Thank you very much, Maria, and thank you very much, Steve, for your respective talks. We're a little bit behind schedule, but we still have something like 20 minutes of time for a discussion. And I cannot fail notice that both Stefan had some questions already in advance, or rather comments for Steve and Maria. And Maria, in your presentation, Steve, you've had at least a couple of points where you pointed out that you would like to hear the opinion of Stefan. And some of them, first ones had more to do with specific scientific questions about what quantum computers are good for. Some towards the end were more about, let's say, outreach and education, right? So yeah. Could I maybe ask now, Maria, could you select one or two of your questions which are more scientific based for starters for Stefan to kick off a discussion?
Of the ones that I just raised, you mean?
Right, just select one.
Yeah. I might, Stefan, I think you already have commented on this, but anyway, you know, from the bank and as well, being part of a group of researchers that would like to, you know, help on this Monte Carlo for option pricing, what would be your advice? You know, first, do you agree that this loading the distribution, you explained that very well, is a challenge? And what are the methods, the alternatives you are thinking about for solution? Or what could you advise to us you should be looking at this or try to do this, or these problems, yes, but this never, you know, whatever you can bring light to us, that would be great.
I think that two steps to that. The first is, well, what are the problems that are challenging classically? I mean, you don't have to use a quantum computer to price a European call option or something like that. Like, I think that's really in pricing, but also in machine learning and optimization, really identify what is really the problem where you think there is a potential, or where, I mean, sometimes it's also large leverage and a small improvement would have a big impact. And start identifying that where really an impact is, and then try to model it. I think particularly for these quadratic speedups and for this quadratic speedups in fault tolerant quantum computers, since the quantum computers are running at this lower or are slower per operation, you need to very carefully analyze the constants in the scaling and not only the asymptotic scaling. And going into this, really looking into how this can be done in detail, gives you an idea about where the bottlenecks are. And I think this is how you build up intuition. This is how you understand the building blocks and what might work and what not. But it also it also guides you. It also helps you identify, okay, this problem maybe turned out not to be the best one to get started, but now you have your subject matter expertise and can think, okay, this is now a criteria on that problem that I have to take into account. What other problem might be better suited? And I think that kind of also touches on the question by Jordi from the chat. Problems that I think, and we also have a paper on that, I think are more suited. For example,
Stefan, maybe if you're gonna answer the question, maybe just I'm not sure that everybody's looked at the Q&A.
Okay.
Just high level the question was.
Yeah, I think that the last part of the question was more generally, could you comment in which situations it is interesting to go to very high precision in finance? So this is in risk, like in risk analysis, you need lots of samples classically, because you're kind of looking for rare events which potentially have a huge impact. And to reliably simulate that using Monte Carlo simulation, or estimate that with Monte Carlo simulation, you have to have a huge number of samples. And that's on one hand side, of course, good, because it makes the classical problem more expensive, though there's maybe a bit more to gain in terms of computation time. But on the other hand, there's I haven't mentioned this, but there's a very interesting property of amplitude estimation, and that is it gets more accurate towards the extremes. Like you always have to normalize, so you're always estimating a property that is between 0 and 1, and if you are and you have to normalize your model accordingly. But if the result tends to be closer to 0 or closer to 1, then amplitude estimation tends to get more accurate. Because it's applying, there's a mapping at the readout, and that's causing this behavior. So on the one hand side, these rare events are more difficult classically. On the other hand, these are kind of the sweet spot for amplitude estimation. So looking into risk and tail measures might be I think is a very interesting direction. And of course, is very important. I mean, on the one hand side, from a regulation perspective, but also I think from an operational perspective, I guess. But here, Maria and Steve probably know better. You want to know the risk that you are taking, and the better you can do that, the more informed decisions you can make.
Thank you very much. So Maria or Steve, if you have a follow-up question, of course, that's the most interesting for the panel since we have you here. But maybe if you're still cooking that, maybe I forward another question, slightly different from Marius, who is asking about the quantum feature maps in the context of machine learning. And I have to admit, I was also interested as well. Like, do you think the quantum feature maps that are used right now in quantum machine learning are the ones that are going to be used later? And maybe if I can add, and is there anything special to supervised learning problems in finance that would make you believe that the quantum feature maps will be sort of particularly well suited?
Mm-hmm. I think this is one of the core questions at the moment. The feature maps that we currently use are mostly motivated by the fact that they are difficult to simulate classically, not that they have any practically relevant feature that make them particularly suitable for any application. So this is really to have an end-to-end argument that this machinery can do something that has a potential to, or can do something that a classical computer cannot do. Whether this leads to a better classification, that's a second question. But this was so far the motivation for the design. And interestingly, for all the test case, or for many of the test cases that we looked in, it worked particularly well. So I think it's quite surprising how well it worked, given that it's like really not designed for performance, but designed for being difficult classically. But we see problems where this where they are not working too well, and there's a recent result of colleagues of mine that looked into kernel alignment. So we don't start with a fixed feature map, but with a parameterized feature map, and then you train this feature map and align it to your data. I think it's kind of something. Can think of it a little bit as something in between a fixed feature map support vector machine and a quantum neural network with maybe a repeated encoding. If you have something in between, then you have a kernel that you align to your data. Particularly because we don't really know how to design the feature map yet, so we design it a little bit more generally, and we then fit it. And yeah, so to your question, I think we will see completely different feature maps coming up. Why? Because they haven't been designed for particular problems, but just for being difficult. And another point is it was on the slide, I didn't mention it on the roadmap. There's also new capabilities in the hardware coming up, like things like dynamic circuits. If you measure and then you adapt your circuit based on the measurement, for example, this also allows you to do new things. And I think we don't have such a good understanding of what this means in terms of feature maps. I mean, it's crucial for error correction. So that's why we definitely have to get that done. But I think it also allows us to do more types of circuits, and therefore maybe also more types of feature maps that might work better in certain cases.
Thank you very much, Stefan. I'm noticing a question for Maria, if you're up for it, from Jordi. He's asking, is it in principle possible to somehow recycle the data generated during your large big Monte Carlo simulations that you described, since he's guessing that not all of the 50,000 risk factors necessarily change overnight, or do you really have to go from scratch every single time?
No, it's a very good question. And when I was pointing out that, of course, we do some simplifications and approximations that could be done. I just described there a very raw problem in which, with no further thinking, I just describe, if we move this, we need to repeat everything. But of course, you can do that wisely. And not only that, for the sensitivity computation problem that I then describe, there are other techniques like American Monte Carlo, where the pricers are approximated with some regression. So then at the end, instead of using the Monte Carlo, you just reprice quickly. However, any approximation that is not exact comes with some error, with some less accuracy, and that involves that for us that need to face regulators and etc. We need to monitor, we need to measure, and that involves further work. So in this case, if the quantum computers could bring, the possibility of not requirement for this approximation, that could be better. But of course, some work on that could be done. And I would like to take this opportunity as well to ask further to Stefan, because from the problems that you described with the optimization, in which you took the best classical solution and then went further. And as well, I believe that with the machine learning as well, you can reach out to solutions that they cannot be achieved with the classical. Maybe the simulation problem, at least for now, we are not formulating the problem in the same way, at least myself, because I was formulating for you a problem that was just not that I cannot compute the solution in a classical. It is just that it's too heavy, it's too big, but I know. So maybe it's the wrong question. Then what I should try to ask for a quantum computer to do is more a problem that I really cannot resolve in the classical. So, and for those, they will bring. So, you know, I don't know. I think that, of course, there is no a solution, and we will have examples of both, but I would like to get your opinion.
So I mean, one fundamental difference between the optimization machine learning and the Monte Carlo simulation is that in the one case you can very easily verify that you found something that's better, because you have a loss function or an objective function. You can just plug it in and see, okay, I get a better value. And just because the risk gets smaller by your estimator, this doesn't necessarily is a good thing, right? You want to measure it precisely and not like have an algorithm that just tries to minimize it somehow. And this makes it so difficult, I think, and that's also the reason why we haven't found any near-term compatible algorithms. And modeling, it takes too much resources in the quantum circuit.
Thanks.
So, Stefan, I noticed that you're following Q&A, and we have a very technical question from David. If you're willing to take it up, he says that many say that pricing of multi-asset derivatives or path-dependent derivatives might be the most promising with respect to quantum advantages. Yet you show that the thresholds for a two-path-dependent derivative are high. So which kinds of derivatives might be most promising then for quantum advantage, in your opinion, and whether there's any chance for them to be sort of NEASQ friendly?
So I think adding some risk component somehow to it. You can also have market risk. I think Maria also mentioned sensitivities earlier. I think this adds further complexity, and there will actually be some publication coming out next week. You can have an eye on that, which makes I think a big step towards this direction. And this helps. Like this is on the one hand side makes it more difficult classically. On the other side, can be a sweet spot on the quantum side. And I think these are the directions that I currently see. And we looked into credit risk analysis of large portfolios, like with million assets or something like that. And then we could show that in principle you could do this somehow in almost near real time. So I think this is more a direction like having larger things like many assets, and then adding a risk component to your problem, like looking at the tail. I see that you ask about stochastic volatilities. No, I'm not necessarily asking about meaning stochastic volatilities. That's also something that we could add, but I'm more saying like, how vulnerable are you against changes in your assumptions or changes in the parameters of the market or things like that? What's your sensitivities, like estimating sensitivities?
Very, very interesting answer, Stefan. Thank you very much. Unfortunately, this brings us very close to the end. We're running out of time. All good things end, and I would like to actually give a chance, or rather, a question to Steve, sort of for the closing of our session. I was particularly piqued by the point that you said that you very often have people come and tell you, I have this method for doing this and that, and then you're the one who filters noise from signal. So maybe if you would like to take a chance to say something to us from the quantum side, or maybe direct a question to quantum quantum expert from your perspective.
No, I think maybe from not a non-quantum expert, we need to understand the technology, understand what it means, and it can get very fuzzy for people. And I think part of what we're trying to do is kind of explain it. I've got people like, there's this, well, it'll never be achieved because it's quantum physics, and then others that are committed to do that. So I think It's interesting to see this space, see what's evolving, and really understand it. So I think education is big, and I can tell by the questions coming out of this forum, it's a very technical crowd. So the only question I saw for me was I providing slides or not? And which is okay. Typically I go to forums and I just keep getting asked questions. So I was really happy that both Stefan and Maria here were to cover that. So I think part of what I'm looking at is curiosity, keeping an open mind and learning, because part of innovation is it's always changing and it's always growing and technology is getting better. And I'd love to see a lot of this materialize.
Thank you very much. And with these words, I'm handing over the spotlight to Pascal.
Well, thank you. Thank you very much to all of our speakers. Thank you to our attendees for staying with us this Friday evening. I think we got lots of questions, actually too many for the time we had. But thank you anyways. Thank you, Vedran, of course, for moderating this. You're a fantastic moderator, I must say. So we hope to welcome you at our next webinar. It's on Wednesday, next Wednesday. If you have an interest in this, in quantum optimization algorithms for mesh segmentation, and that's all. Bye bye, and hope to see you at the next webinar. Thank you.
Have a great week. Thank you.
Okay, so I have stopped recording, and yeah, well, thank you again. I think many people stayed until the end, although this was Friday evening. So thank you very much. I will close for now.